Our next speaker is Benjamin Joachimi, who will present a talk about SBI meeting reality. You have 3 minutes.
Yeah, great. Okay, so I would briefly like to highlight work that some of my brilliant PhD students have done. And this is all centered on simulation-based inference and more the realism of it. And so the context, the motivation can maybe be understood by this chart here. So it's about the technology adoption and the readiness towards it. We're probably on the left-hand side here, mostly. But if we want to have maximum impact and if we want our methods to be used, we have to reach the bulk here. Okay, so the astronomer on the street. And how do we do that? And so to convince them, it's not just about performance, but also increasingly about the ease of use, how easy are our methods to use, how reliable and robust are, and we heard about it in previous talk already. And of course the cost. For us it's mostly computational, but earlier today we already discussed about environmental costs, for instance, as well. And so we've done this in the context of gravitational lensing, the large-scale structure, and we focused more on the right-hand side this time. So we did not, or not yet, engage with higher order statistics and getting more information out of the universe. We just want to do exactly what the standard analysis does, and we want to reproduce it exactly and do more, do better, and show this to everyone and convince everyone. So that is the context. How we do this is, if we just want to get normal two-point vanilla statistics of large-scale structure, we can build specific simulations that are very, very accurate, actually more accurate than your typical n-body simulation in just that statistic, and cut corners for other effects. And this is what we've done here. So we simulate directly on the shell, and we've combined this with an approach that simulates realism of the survey. So we can essentially, every part of the sky can be its own survey with its own galaxy population and properties like complicated things, even PSF ellipticity of your survey in there. And all of this in a quite effective way, so you can run it from scratch with all the simulations in a day's time on your normal institutional HPC cluster, which is comparable to a classic Gaussian likelihood analysis. And so when you do that, we actually find that we can exactly reproduce the posterior that you get. This is an 11-parameter analysis. This is exactly what the kilodegree survey, the most recent analysis, has done. And we can reproduce this when we impose a Gaussian likelihood, which of course the classic analysis does. And now we can do more. We have all the opportunities to do validation and extra bits for this. And just to highlight one example here, this is what you see here on the left. This is still on simulated data. We're still blind to this. You see 3 cases here on the left. In orange, you see the SBI analysis with neural likelihood estimation. And then in purple, you see a classic analysis where we have Gaussian likelihood analytic model. And in the middle, you see an SBI analysis where we have forced that the likelihood to be learned is a Gaussian. So what it learns from simulation is the spread, so the covariance, but also how all of this links to the cosmology. And what you see here is that overall, you get fairly good agreement. So what that tells us is that the Gaussian likelihood is still a fairly good assumption for the current generation of surveys. But you start to see some subtle differences here, and in particular in parameters like S8 up there, where it starts to matter and where we're really interested in. And this is where the future, I think, of SBI lies, and this is the kind of analysis that we can hopefully convince the community with. And so this was mostly done by these 2 people here, Max, who's now a postdoc, giving his services to Euclid, and Karyam, who's done lots of the methodology development, including more validation, goodness of fit statistics for SBI, and working also on wavelet harmonics together with Jason. And best of all, he's writing up his thesis, so you can hire him from next year for your work. Okay, and I'll stop with just highlighting another student with whom we're applying this now. There's a nice bell. To earthquake locations, so there's more applicability here. Thank you.
Thanks, Benjamin.